Imagine a world where every drop of energy is counted, where the simple act of walking your dog, the morning jog, or the bustle of a busy street corner contributes directly to powering our lives. Today, we explore a quietly radical idea, that the jiggles, shakes, and everyday motions around us are not just noise or waste, they're potential sources of electricity. Can we realistically capture that scattered motion, and could it meaningfully power off-grid systems? First, what do we mean by everyday motion? It's the broad sweep of mechanical activity all around us. Footsteps in a station, cars on a bridge, the vibration of machinery, the flow of a stream, people dancing, and even the subtle movements of our bodies. These activities convert chemical or kinetic energy into motion that usually dissipates as heat or vibration. The question is whether we can intercept some of that flow and turn it into usable electricity. A few technologies already attempt this. Piezoelectric materials generate charge when stressed and have been used in demo installations. Dance floors that light up, pressure tiles in transit hubs, sensors embedded in footwear. Triboelectric generators harvest charge by friction and are showing promise at small scales and in flexible formats. Electromagnetic harvesters convert motion into current using magnets and coils, often found in larger-scale retrofit solutions. And in moving water, hydrokinetic turbines capture the steady, continuous motion of a river without the need for dams. Each approach has different strengths. Piezoelectric and triboelectric are compact and well-suited to wearables or flooring. Electromagnetic systems can be efficient at larger displacements. Hydrokinetic systems deliver continuous power where there's a reliable flow. To make this practical off-grid, we need to think beyond a single device. Off-grid systems have to be efficient, reliable, and self-contained. They often combine solar, wind, and sometimes micro-hydro with batteries and controllers. Motion capture can add resilience and diversify energy inputs, but only if it's integrated smartly. That means matching the strengths of motion harvesters to loads they can realistically serve. Low-power lighting, sensors, charging small batteries, or supplementing other renewables during peak demand. Consider a remote village as a concrete example. Pathways lined with pressure-sensitive tiles or low-cost kinetic plates could collect footsteps during the day. The energy yield from a single step is small, typically a few joules or milliwatt hours, but cumulative foot traffic can yield useful bursts of power for LEDs, phone charging stations, or to top up a community battery bank. In places where diesel generators are the default fallback, even modest, locally generated energy can reduce fuel use and improve quality of life. For continuous needs, pairing footfall capture with a small hydrokinetic unit in a nearby stream could smooth supply. The river provides steady baseline power. Motion capture supplies variable bursts during busy periods. We're already seeing real-world pilots that illuminate possibilities and limitations. Some cities and venues have installed energy floor demonstrations that power displays or lighting in high-traffic zones. Gyms with energy-generating exercise bikes and dance clubs with capture floors turn customer activity into part of their electricity budget. In the water sector, small hydrokinetic turbines installed in canals or river bends can produce hundreds of watts to kilowatts, depending on flow, enough to run lights or recharge batteries for off-grid installations. At the personal scale, wearables and portable devices are a fast-moving frontier. Advances in triboelectric nanogenerators and miniaturized electromagnetic harvesters mean that motion-powered watches, health monitors, and emergency beacons are increasingly viable. This is particularly useful in disaster zones or remote medical applications where conventional charging is sporadic. A sensor that keeps itself alive from ambient motion can dramatically extend the usefulness of critical monitoring equipment. But there are real technical and economic challenges to reckon with. Energy density is the biggest. Motion harvesters tend to produce low power relative to the size and cost of the installation. A single footstep may generate only a few joules, useful when multiplied across thousands of steps, less impactful for continuous high-power demands. Storage is another bottleneck. Capturing intermittent motion requires batteries or capacitors, and current storage tech adds cost, weight, and environmental concerns. Durability and maintenance matter too. Moving parts, flexible tiles, or underwater turbines must withstand wear, weather, and sometimes vandalism. Finally, the upfront cost and life cycle environmental impacts of manufacturing and installing these systems can offset some of their benefits if not managed carefully. So how do we move beyond novelty to useful deployment? One approach is targeted placement. Focus motion harvesting where motion is concentrated and predictable. Transit hubs, stadium entrances, school corridors, gym floors, and pedestrian bridges. There, per-step yields accumulate and justify investment. Pair harvesters directly with low-power, high-value uses. LED street lighting, wayfinding displays, charge points for phones or radios, or sensor networks that improve local services. Design the system as a complement, not a primary source. Hybridize with solar, wind, or micro-hydro, and use smart controllers to direct motion-derived energy to flexible loads or to charge batteries during peak foot traffic. Another pragmatic step is reducing demand to match supply. Off-grid communities benefit most when loads are tailored to what harvestable motion can reliably provide. Energy-efficient LEDs, low-power sensors, and demand-side management that schedules higher consumption for times when motion activity peaks. Community engagement is crucial here. If people know their steps power a village pump or street light, they're more likely to support and maintain the system. Behavioral nudges and gamification can even increase participation, turning energy generation into a shared local activity. Research and materials science are also advancing. Improvements in piezoelectric materials, more efficient triboelectric designs, and tougher, lower-cost polymers extend lifetime and lower costs. Energy electronics, power conditioning, low-loss converters, and better controllers help squeeze more usable power from intermittent sources. At the system level, modular designs that are easy to repair and upgrade lower lifecycle costs and increase social acceptance. There are social and ethical angles as well. Deploying motion harvesting in public spaces raises questions about monitoring, sensors collect data, equitable benefit, who profits from the generated energy, and aesthetics. People are more likely to accept technologies that are unobtrusive or that visibly return value to the community. Successful projects often pair technical rollout with clear local benefits and transparent governance. So what kind of impact can we realistically expect? Motion harvesting is unlikely to replace solar or wind as bulk power sources, but it can make a measurable difference in niche applications and in resilience. In off-grid settings, it can reduce generator run times, extend battery life, and provide critical power for lighting and communications. In urban areas, it can offset small but meaningful amounts of energy in high-traffic nodes and foster public awareness about energy flows. The greatest potential may be cultural and systemic. By making energy production more visible and participatory, these technologies can change how people think about and value everyday energy use. In the coming segments, we'll dig deeper into the mechanics, how piezoelectrics, triboelectric generators, electromagnetic harvesters, and hydrokinetic turbines actually convert motion into electricity. And we'll examine case studies that reveal what works and what doesn't. We'll also look at metrics. How much power can be expected from a footstep versus a river flow? What storage strategies make sense? And which business or financing models enable broader adoption? This is a story of small forces adding up. Capturing the tiny energies we generate naturally won't single-handedly power cities, but it can power choices, cleaner alternatives in remote areas, added resilience when conventional systems fail, and a shift toward more thoughtful energy design. Keep watching as we uncover how the hidden energy in everyday motion can be marshaled, one step, one ripple, and one innovation at a time, to help create more resilient, decentralized, and engaged energy systems.